for today's lesson, we're going to look at section 7.3. This is just day 1 of 2 days. We're going to break this up into 2 different parts. This is page 444, and what we're going to do now is we're going to look at transformations of just the sine and cosine graphs that we talked about yesterday. So what we're going to be looking at, and I'm going to notate this a little bit differently than the book, we are going to be looking at y is equal to a sine of b times x minus c plus d, and y equals the same thing with cosine. Each of these numbers represents, or each of these letters represents a number that is going to be introduced to our equation, which creates a transformation. What we're going to do today is we're going to talk about A, B, and D only. We're going to talk about C tomorrow. So this is all we're talking about today is A, B, and D in these 2 forms. So the first thing I want to talk about is A. A represents your amplitude. Now, technically, the amplitude is the absolute value of A. I mentioned to you yesterday that amplitude is always a positive number, hence the absolute value. If A ever appears to be a negative number, or if A ever is a negative number, then that means that you have an additional transformation, and we'll talk about that. But it is not part of the amplitude. So what we're talking about with A is we're talking about something like y is equal to 2 times sine of x. Notice the 2 is sitting in the A position. It's being multiplied by the sine curve out in front. Therefore, this tells us that our amplitude is equal to the absolute value of 2, which is just 2. Our period has not changed here. All we're doing is we're changing one component, one parameter, in this case the amplitude. So our period for our sine curve is still going to remain 2 pi. The way I want you to graph this is I want you to graph this on your x and y axes, and what I want you to do again is I want you to go out to 2 pi for the period. Go out a reasonable distance, cut it in half to get pi, cut it in half again to get pi over 2, 1 pi over 2, 2 pi over 2, which is pi, 3 pi over 2, and then 4 pi over 2, which is 2 pi. That will give us 1 period of our sine curve. Now, our normal sine curve, y equals just the sine of x, goes between 1 and negative 1. And it does this: beginning, middle, end, maximum, minimum. And so normally what it would do is it would look like this. This is what we drew yesterday. Nice smooth curve. Again, make it solid, not dotted, but dot it first and then go back and make it solid. It makes it easier. I'm just not going to do that on the board. It's a little bit too difficult to get it to look nice. So now we're going to change our amplitude to 2, which means that instead of going between 1 and negative 1, it's now going to go between 2 and negative 2. What does that do to our curve? Well, what that does is it doesn't change our center points, but it doubles our y-coordinate, which makes these go to 2 and negative 2 instead of 1 and negative 1. When you double 0, you still get 0, so that's why those stayed where they were. And so now what your curve is going to look like is it's going to be steeper. Again, this corresponds, if we were talking about sound, this corresponds to a louder sound. It still has the same pitch because the period, the frequency, the wavelength has not changed. But this is what your curve would look like. And so we are going to be, again, showing each of our transformations. And so I'm going to need you guys to indicate to me, preferably using colors, but otherwise you could use dotted and dashed and little X's and little dots, you know, whatever you need to do. You guys need to indicate to me which one is the final graph because I want to see the transformations. Now, having said that, it is perfectly fine with me when you guys draw this particular curve to not start with the basic parent function. It is perfectly fine with me if you guys take care of amplitude and period with your numbering system, your scale. And so what I would actually do is I would actually do it this way. Here's 2 pi. Here's pi. Here's pi over 2. 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2. Maximum, minimum. But instead of going 1 and -1 and then making it steeper because that gets difficult to draw, just number this as 2 and -2. And that is perfectly acceptable with me because it shows me you understand what the amplitude is representing. Now, beginning, middle, end, maximum, minimum. Sorry. Try and get this to look reasonably nice. There is your sine curve. So that's y equals 2 times sine of x. Okay? That's our amplitude. Now let's take a look at what B does. B is our period adjustment. Notice I did not say it is our period. It is our period adjustment. It's going to change our period. So for example, we're now talking about y is equal to sine of 2x. Notice the 2 is not in front now. Now it's part of the angle. We're taking the sine of double whatever x is. So if x is 30 degrees, we're now taking the sine of 60 degrees. 2 times 30. This is B. This is our period adjustment. And the way this works is that the new period, and you want to make sure that you write this down, the new period is always equal to the old period divided by whatever B is. This is your equation for relating old period, new period, and B. Now, our new period is equal to our old period, which for the sine curve and for the cosine curve, our old period is 2 pi. That's our normal period. Divided by B, in this case, B is 2. And so that means that our new period is going to be 1 pi. Notice our amplitude, there's no number there, so it's really a 1. Our amplitude is going to be 1 on this one. And like I told you on the last example, it is perfectly okay with me that these transformations you do not need to show me separately. Now let me show you separately what they would look like, and then I'll explain why I don't need you to draw it that way. And I'll show you how I want you to draw it. So here we go. Here would be our normal parent function. Sine, beginning, middle, end, maximum, minimum. This would be our parent function, y equals sine of x. If we're going to look at y equals sine of 2x, now our period is pi. So now we've got to take pi, cut it in half, cut it in half again. Half of pi over 2 would be pi over 4. So this would be 1 pi over 4, 2 pi over 4, 3 pi over 4, and 4 pi over 4, which is just pi. Now we'd have beginning, middle, end, maximum, minimum. And so now what our curve would look like is it would look like this. What's happening? Well, the speed of our curve has doubled. We doubled x, so we doubled the speed of our curve. In other words, where it used to take us 2 pi to get through one full cycle, one full period, now it only takes us half of that pi. Which means in the old space, do you guys see that I could actually draw 2 entire sine curves? 2 entire periods instead of 1 because it's moving twice as fast. The problem is that this becomes difficult as we squeeze our x direction down smaller and smaller. It becomes problematic to draw this thing, especially if we also have the amplitude changing to 5 or 6. You end up with a curve sometimes that ends up looking like this. And it's very difficult to draw and get any information from it. So don't do that. What I recommend that you do, and this is perfectly acceptable with me, these are the only transformations that you can combine right from the get-go. You don't have to start with the parent function. What I would do is this. I would say, okay, my amplitude is 1, so I'm going between 1 and -1. My period is pi, so I'm going out to pi, cut it in half, pi over 2, cut it in half, pi over 4, 1 pi over 4, 2 pi over 4, which is pi over 2, 3 pi over 4, and 4 pi over 4, which is pi. Beginning, middle, end, maximum, minimum. This way I can draw a correct one period of my sine curve, but I do not need to worry about squishing it down or stretching it out. This would be the graph of y equals sine of 2x. Okay. Now, if we were dealing with y is equal to sine of 1/2 x, then what would happen there is you would take 2 pi, the old period, divided by 1/2, which becomes 2 pi times 2 over 1. And now your period would be 4 pi, so you would be at 1 pi, 2 pi, 3 pi, and 4 pi as your 4 marks there. But you would still just draw at the same size, you just adjust the scale of the axes, and that will reflect the proper period. Okay, the next transformation is C, but that's going to be tomorrow. So we'll talk about that on the next lecture. So the next one we're going to talk about today is going to be D. And D is your horizontal shift. Excuse me, your vertical shift. Sorry about that. D is your vertical shift. So now we're talking about something like y equals sine of x plus 2. Go back to what you knew about transformations from earlier in the year. When you had something like y equals x squared, which is your basic parabola, and you added 2 to it, what did it do? Well, that was a vertical shift. It moved your whole graph, all your guide points, up 2 units. This does the same thing. Okay? So this is going to be a vertical shift, and it's going to be exactly what it looks like. Plus goes up, minus goes down. And so what we're going to do here is we're going to still notice that our period is our normal 2 pi, and our amplitude is our normal 1, because I'm only changing the vertical shift right now. So here I do want you to draw the parent function, but again, the parent function will involve the period and amplitude of whatever the equation tells you. There's no adjustment needed here, so these are going to be our pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, and our 1 and negative 1. Beginning, middle, end, maximum, minimum. Here we go. So there's our parent function. Now what we're going to do is we have to shift up 2 units. So this is going up to 3. So each guide point, I'm not going to shift the whole curve. I'm going to shift each guide point and then draw the curve. So 0 moves up to 2. 1 moves up to 3. 0 moves up to 2. Negative 1 moves up to positive 1. And 0 moves up to 2. And now this is my final graph. And you need to indicate to me, in this case, that the red one is the final one. Again, I'm only graphing one period. That's sufficient. It shows me that you know how this works. If you can draw one, you should be able to draw as many as you need to. So this is your vertical shift. Now, the vertical shift is always the absolute last transformation that you do. The last transformation. Last transformation. Get the idea? It's not the second, it's not the third, it's not the fourth, it's the last transformation, no matter what. That's going to become extremely important when we talk about our secant and cosecant curves. Because if you do this prior to anything else, you run the risk of getting the wrong answer when we get to secant and cosecant. So just make sure that this is always the last transformation. We'll talk about the order of the other ones in just a minute. Okay, now what I want to do is I want to talk to you about what happens if you have a negative a value. For example, y equals negative 3 times sine of x. I told you before that the amplitude is really the absolute value of a. Okay, so negative a, I don't really mean that we're going to glue a negative onto a. A is really a negative number, but I'm going to label it as negative a. So the amplitude is negative 3, which gives us 3. So our amplitude is still a positive number. What the negative does is the negative indicates that you have an x-axis reflection. Remember that when you had y equals x squared, that was a parabola that went like this. When you had y equals negative x squared, that was a parabola that went like this. It flipped it over or reflected it over the x-axis. You don't want to think of it as upside down. You want to reflect it over the x-axis. Okay, so that's the idea. So this is very simple to do. Notice I don't have any other transformations going on here. My amplitude, excuse me, I do have one other transformation. We transformed our amplitude already though. There is no period change. The period is 2 pi. There's no vertical shift, so we don't have to worry about that. So again, you can take care of your amplitude and your period when you set up your scale. So this is going to go between 3 and negative 3, going out to 2 pi, half of that, pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, beginning, middle, end, maximum, minimum. Here you go. There's our parent function with the amplitude and period indicated. Now we have to do our x-axis reflection. And how do we accomplish that? Let me change colors. Well, if I reflect this point over the x-axis, it stays the same. If I reflect this one, it stays the same. If I reflect this one, it stays the same. Notice I'm not reflecting the whole curve. I'm reflecting one point at a time. This one was up at 3. When I reflected over the x-axis, it drops down to negative 3. And my negative 3, likewise, reflects up to positive 3. And so now this is what the x-axis reflection looks like on our graph. Sorry, I missed a little bit, guys. I should have been there. And again, red is our final. Questions about that? And again, what I would do is make sure that you go back. Make it solid. There we go. So that's how an x-axis reflection occurs. You can also have y-axis reflections. We're not really going to deal with those right now. You don't have to worry about those at this point in time. Okay. Now what I want to do is I want to put a number of these together. And so let's take a look at what happens when we have something like this. Let's throw everything at you. Y is equal to negative 4 sine of 3x plus 1. The first thing that I want you guys to do is I want you guys to identify each of your transformations. The negative in the front is going to be an x-axis reflection. The 4 means that our amplitude is now going to be 4. The 3 means that our period, our new period, is now going to be 2 pi divided by our b number, which is 2 pi over 3. And then the plus 1 means we're going to move up 1 unit. These are our 4 transformations on this particular example. The order that you want to do them is you want to start at the x and do anything that's attached to the function with the x. So we're going to take care of this first. And then we're going to, since this is also attached to sine, and because it involves our numbering on our axes, we're going to take care of this, first as well. So again, just like before, we are going to take care of both the amplitude and the period first. Then what we're going to do is we're going to work our way forward, and second is going to be the x-axis reflection, And then last is going to be the vertical shift. Notice I did not call it third because I want to drive it into your brain that that is the last thing that we do. Not the third thing that we do, it's the last one before we move on to the next problem. Okay, here's how I would graph this, and then we'll take a look at a cosine one and get you guys going. So, this right here is 2 pi over 3. Half of that is pi over 3. Half of pi over 3, when you cut something in half, you're multiplying the denominator by 2. So this is going to be pi over 6. So this is 1 pi over 6, 2 pi over 6, which becomes pi over 3, 3 pi over 6, which is now pi over 2, and then 4 pi over 6, which is 2 pi over 3. So now we've taken care of our period. Now we're going to take care of our amplitude. We know that this thing is going to go between 4 and -4. So that takes care of our amplitude. So I'm going to draw my parent function in with the proper period and amplitude. Beginning, middle, end, maximum, minimum, so now we took care of these two transformations. So now we're going to take a look at the second transformation, which is our x-axis reflection. I'm going to change colors. When I reflect over the x-axis, the zeros stay at 0. The 4 reflects down to -4. The -4 reflects up to +4. And now I have this one. Hopefully the colors are coming out well on the recording. So now the blue one is going to be our x-axis reflection. The last thing we have, and I'll go to red for this one, is our up 1. So now it's very important, guys. I need to put in all my other marks here. You'll see why in a second. -1, -2, -3. Make sure they're spaced out evenly. So now 0 moves up to 1. -4 is going to move up to -3. 0 moves up to 1. 4 moves up to 5. 0 moves up to 1. Now I'm using the red dots, and so now my curve is going to look like that, with the red one being the final. Okay? So that's the way this works. Now, cosine is going to work exactly the same way. The only difference is that we're going to be using 5 different guide points than what we used for sine. So let's take a look at a cosine one, and then we'll turn you loose. So let's take a look at y is equal to 2 cosine pi over 2 times x, or pi x over 2, it may be written as in your book. Sometimes they do that. So again, this could be pi x over 2. It's the same thing. Again, we want, and then we have -3 at the end. Again, we want to identify our transformations before we start. This is going to change our amplitude to 2. This is going to change our period. Our new period is going to be equal to the old period, 2 pi, divided by b, pi over 2. But we don't divide by fractions. We multiply by the reciprocal. So that's 2 pi times 2 over pi. Notice the pi's cancel, and we get a number with no pi's on it. That doesn't change anything substantially the way I taught you to do this. That's the beauty of the method I gave you. If you had to try and shrink or grow this thing, in this case shrink it from 2 pi down to 4, from 6.28 down to 4, it would be hard to know where to put 4 if everything's numbered in pi's. But because we're going to number everything relative to the period, that's not going to be a problem at all, which you'll see. And then finally, this one says we're going to go down 3. So we're going to do this first. We're going to do this first along with it, our amplitude and our period, and then this one is going to be last. But remember, we're using cosine this time. So we have to use those other guide points. Our period is 4, so this gets marked 4. Half of 4 is 2. Half of 2 is 1. 1, 2, 3, 4. That's it. Works the same way as it did with all the other periods. Our amplitude is 2. So 2, negative 2. Cosine begins and ends at the maximum. Halfway it's at the minimum. In between it's on the x-axis. Here is our parent function with the proper period and amplitude. So that takes care of those two. Now we're to our last one, which is down 3. Again, I've got to put my other units in here so that I can see what I'm working with. I have to go down 3. So negative 3, negative 4, negative 5. So I'm going to change to red. If I move 2 down 3, I end up at negative 1. 0 goes down to negative 3. Negative 2 goes down to negative 5. 0 goes down to negative 3. 1 goes down to, 2 goes down to negative 1. Remember, this is a cosine curve, so make this thing curve as nicely as you can. And I'm not a super stickler for this, guys. You just need to make a reasonable effort and tell me which one is your final graph. So that's graphing sine and cosine with transformations A, B, and C, or A, B, and D. We'll talk about C tomorrow.